Yesterday we had finished off by adding 40 to our sine function, and we noted that the graph started here at 40, went up to 65, came back through here, and we noted that this was the midline for that function. It's kind of like a movable x-axis that cuts the graph in half. So we come back down here to 0, and then we move down to this, which we determined was 15 feet. That's the lowest position the car could get to, since we have that platform now. And then it moved back up to 40 feet, 65 feet, and so on. And now take a look at this. We have determined that it's smart to get in at the bottom of the Ferris wheel and not throw each other up to the 3 o'clock position for car 1. So now on our Ferris wheel we're going to get in at the bottom, and that's going to be car 1 at the 6 o'clock position of the Ferris wheel. This is 15 feet. That's the lowest the car can get, because there's a platform there that prevents that car from going any lower. It will still go on up, and then up to 65. If it goes up 25 feet, it's made it to the midline, and if it goes up another 25, it's made it to the very top, which is 65. Well, it is. This is what's coming up next. Off video, we just explained half of what's coming up. But look at the two graphs on the same plane. Starting at 40 feet is the red one. And here's the pointer. That's where we were before. And then the blue one is where we're at now when we start at 15 feet. So how has it shifted? And we answered this off camera, that it has gone to the right. It has shifted to the right. But now we have to figure out by how much. So what should be done to y equals 25 sine theta plus 40 to account for that shift? And off camera we said that if we move to the right, then it's got to be a minus sign. If we move to the left, it's got to be a plus sign. So what goes in that quantity next to the theta? There's going to be a minus sign, but now we have to figure out what it is we're putting in. And off camera we looked at that shift. We had a minimum point here, and then we noted that it moved over this way. It was initially at 3 pi over 2, and then it moved to 2 pi. So what is the difference between 2 pi and 3 pi over 2? Do you know what 3 over 2 represents as a decimal? 3 over 2 as a decimal or as a mixed number is what? Can't hear you. 3 over 2 as a decimal or a mixed number equals what? 1.5. So what is the difference between 2 and 1.5? 0.5. 0.5 as a fraction is what? 1/2. We have to put pi in there. So what does it turn out to be? Two pi minus 3 pi over 2 is? Half pi, which you could write like this, but how do we normally write it? Pi over 2, that is right. So we're going to have to put in watt in this area here. We moved to the right. We knew that was minus. We just found that the distance of that movement was pi over 2. So what do we put in the parentheses? Minus pi over 2. So there is our new function now. This accounts for car 1 starting at the bottom of the Ferris wheel, the 6 o'clock position. This means that we have a diameter of 50, which means the radius is 25. We have shifted it pi over 2 to the right, so we have minus pi over 2. The reason why we have to do this is because car 1 is going to start at the bottom. We have finally discovered that it's easier to get on a Ferris wheel at the bottom than it is any other place on the Ferris wheel. And this 40 in here accounts for when we were at the 3 o'clock position and we had the 25 feet radius, and then plus the 15 feet from for the box. So that car was at 40 feet. But we've moved the graph down and made that shift. The co-height function graphs. Alright, here is the co-height as a function of amount of rotation. So remember when the car was at the 3 o'clock position and the co-height is 25. Here is a Ferris wheel and the car started here and the distance from the center to that car is 25 feet. If you're in this direction for co-height, it's positive. This direction is negative in relation to the x-axis. So it starts at 25 feet when you're at the 3 o'clock position. And then as you go around in the counterclockwise position, you're going back towards 12 o'clock. 12 o'clock is pi over 2. It's at 0 because it's on the y-axis. Then you go out to pi, that's 180. That is this area right here. It turns out to be negative 25. You come back around to the bottom of the wheel. At the 6 o'clock position, you're on the y-axis again, so it's 0. And then we're going to repeat this all over again. That's what we had so far. But now we know that we're starting at the bottom of the Ferris wheel. So finally, we have to adjust the co-height function. If it starts at the bottom of the Ferris wheel, you're on the y-axis, so it's got to be 0. And then when you rotate counterclockwise, you know it's like you're going backwards. Your back is to the movement, the direction that you're going. So we're going to go this way, and then up to the 3 o'clock position, you're at 25 feet. At the top of the Ferris wheel, you're at 0 again because you're on the y-axis. And then back around. We have a negative 25 feet, and then back to 0 again. Here are both graphs together on the same plane. Now remember when we were at the 3 o'clock position, that was the start, at the 3 o'clock position. But now we're starting at the 6 o'clock position down here. If I could spell o'clock, that would be wonderful. There we go. We're on the y-axis at the bottom of the Ferris wheel, right here. So notice what's happened here. We have 0, and then pi over 2, and then this is pi. So it's at pi there, and then it's gone over here to 3 pi over 2. So the difference between 3 pi over 2 and pi is going to let us know how much this has shifted. What is the difference between 3 over 2 and 1? It's what? Yeah, 0.5, that's right. So 0.5, it turns out to be the same thing that we had before. We've moved pi over 2 to the right. And if we move pi over 2 to the right, then what expression has to be put into the function? Minus pi over 2. So let's see. Yeah, we've gone to the right 90 degrees, or pi over 2. That's how it shifted. That's what we did on the last screen. So how should you adjust this function here? And we just answered that. It's going to have to be a minus pi over 2 that goes into the co-height function now. And I've put y equals on this. You can put y equals on any function, but don't forget this originated from x of theta equals this amount there. Alright, so now x of theta, we're putting in 0 for theta. And remember what our function is now. It's 25 cosine of theta minus pi over 2. And let's evaluate what that turns out to be if we put a 0 in here. If I put a 0 in that spot, I should have just put a 0 to start with, but alright, pi over 2 is 90. So we end up with 0 minus 90, which is negative 90. So what is cosine of negative 90? Zero, yes, it is 0. So we end up with 25 times 0, which is 0. So what does that mean for the coheight function? Where are we at when we're at 0 with the coheight? Here's the Ferris wheel. There are the axes. Where am I at on the Ferris wheel when the coheight equals 0? You're at the what? 3 o'clock position. What's the coheight at the 3 o'clock position over here? 25. And what is it when it's over here? Negative 25. What is it when it's here? 0. And what is it when it's here? Now, if we're plugging in 0, that means we have not moved at all. So if we haven't moved at all, we've stayed at the starting position. What is our starting position? 6 o'clock down here. So that means the coheight is 0 at the starting position at the bottom. So that does work out. That means we've tested our function, and it does work out in reality. Now let's test the height function based on what we have so far. And the height function is 25 sine of theta, and we're putting in 0 for theta, minus pi over 2, close the quantity, and then plus 40. Okay, so we know this is 90 degrees. So what is sine? And 0 minus 90 is negative 90. So what is sine of negative 90? It's negative 1. So let's do 25 times negative 1 and then add 40 to that. What do I get? 15. Okay, does that work out? Here is the Ferris wheel. At what point on the Ferris wheel would I be at if I'm at 15 feet above the ground? 6 o'clock position down here. That's the starting position. The platform is 15 feet. So it does work out. Our function is good up to this point. Let's evaluate the coheight function and see if it works out to be at the top. The pi over 2 means we've rotated 90 degrees. Alright, so if we do the coheight function, 25 cosine of pi over 2, which is 90. And remember, the function had a minus pi over 2 in it, so we're taking away 90. Let's see what happens. What is cosine of 0?
1.
Cosine of 0 is 1, so 25 times 1 is going to give me 25. If I move 90 degrees from my starting position, which is down here at the bottom, it puts me right here. And is the coheight indeed 25 feet at that position? Yes, so it's still working out good for that. I didn't hit record on this slide, but we're plugging in pi over 2 for the most current height function, which means we need sine of 0, which is 0. So it cancels that out, and we're left with 40. So if we rotate 90 degrees from the starting position, which is here, we end up there, and it's supposed to be 40 feet off the ground. And we know that 25 feet plus the 15-foot platform down there is indeed 40 feet. Now we're going to do one more thing. It is more useful to track a car as a function of time rather than a function of turns. So that means that instead of tracking it in terms of how far we've turned in terms of degrees or radians, we're going to do it in terms of how far of a turn have we gone? And remember, at the beginning of the problem, it was 2 turns per minute. So instead of a graph that's going to have pi over 2, pi, 3 pi over 2, and so on, we're going to have it in terms of time, which will be in terms of a minute. 2 turns per minute. So here we go. Let's section this off here, even though it may come up on a next slide. If it does, then we'll take it out. We're starting here at the bottom. 2 turns per minute. That means if I can go all the way around this thing twice, and that will equal 1 minute. How long does it take to go around for 1 turn? 30 seconds. So 1 turn would be 30 seconds. If I divide 30 seconds by 4, then what is that? 30 seconds divided by 4. 7.5. So what does that mean in terms of this Ferris wheel? If I start off down here at the bottom, after 7.5 seconds, where am I at? You're at right here, 3 o'clock. At 15 seconds, where am I at? At 12 o'clock. And after 22 and a half seconds, where am I at? 9 o'clock. And then after 30 seconds, I've come back down to here and I'm starting over again. And I'll do the whole thing all over again. And you can add more time to that. 30 seconds plus 7.5 seconds is 37.5 seconds to go back through here a second time. That's how we're going to change our function in terms of time. Remember what I just showed you on the Ferris wheel on the previous screen. If we start off at 15 feet, right here, the starting position, and we go up to the maximum and then back down to the minimum, that means we've made 1 complete revolution. That is 30 seconds. Now down here it says 0.5. The 0.5 is in terms of what? 1 minute, right. So here's 1 minute, here's 60 seconds. If we do it again, go around one more time, we've made 2 revolutions in 1 minute. Here's what it equals in terms of radians down here. Here's 0, here's pi, 2 pi, 3 pi, and so on. We know that 2 pi is 1 revolution of a circle. If we've gone halfway around, we've reached the maximum. We come back down another half turn, and we're down at the starting position again. So this is what the graph would look like, adjusting the x-axis for minutes. Half a minute, whole minute, that's 2 turns, a minute and a half, and so on. You can graph those out for as long as you need it to go. So now we have to write y equals 25 sine of the quantity theta minus pi over 2, close the quantity, plus 40 as a function of time. We're going to take out the pi over 2 and we're going to insert something that's going to be more beneficial to us. So now we come up with this. Y equals 25 sine of 4 pi times the quantity t minus 1/8, close all quantities, and then plus 40. What we're going to do next is inspect how we came up with the minus 1/8 and then the 4 pi on the outside. Remember, this is A for the 25, the 4 pi is the W, this is the phase shift H, and this is the constant K. What we're going to do now is figure out how we came up with that. We're going to work it backwards. We're going to look at why we have 4 pi and then a 1/8 now in this function. It must be in terms of time and not degrees or radians. So we've looked at this and discovered that it had to be 4 pi and 1/8. But why is that? So here is the graph Down here, this is half a minute, a whole minute. Notice you have 2 complete revolutions in a minute and a half, and 2 minutes. Look at where pi over 2 was at on this. Remember pi over 2 that was in the function, it was minus pi over 2. Here is where pi over 2 is at on the x-axis in relation to all of this. Now pi over 2 is directly between this and this that I've just highlighted in pink. So now take a look at this. If this is 1 minute and there's a half a minute, we can break this up in terms of fractions. Like how many of these, and I'll zoom in on it, how many of these distances, if I can bring it back, how many of these distances can I fit into that area from here over to there? Let's inspect that first. You have 1. This is the same thing. There's 2. How many would be in this area? 2. So now how many do we have? We have 4. And then this would have another 2. So this would be 6. This would have another 2. So this would be what? 8. And we only have how many of these that we're paying attention to? 1. So there are 8 of those within the 1 minute span, and then we have just 1 of them. So can you see where the 1 over 8 came from for the fraction? Alright, so let's go down here. Remember the phase shift was pi over 2? So we found pi over 2 on this graph that we've also overlaid the time on, and we found the fraction of 1 minute. Remember 1 minute is 2 revolutions. Alright, so now you have to do the math on this. Look at where the 4 pi came from. The 4 pi came from 2 rotations of the Ferris wheel. We can't forget that, and we can't leave it out of this. The Ferris wheel rotates twice. Twice in terms of radians is 4 pi. And we only had 1 or half pi there that we were paying attention to. Remember the shaded area I shaded in, and then we counted 8 of them. We have 1 of those, which is pi over 2, and then we had to put that over 4 pi because it was 2 complete revolutions. Now simplify that. If you do, it's pi over 2 times the reciprocal of this. That's how you divide by something. It's the same thing as multiplying by the reciprocal. Pi over 2 times 1 over 4 pi. That's 8, or that's pi over 8 pi, and look what it reduces down to. 1 over 8. There's your fraction. Now, will the coheight function change? Yes or no? Does anybody say yes? He says yes. Anybody say no? Alright, let's go. Yes, it's going to change. The coheight function is going to change the same way that the height function changed. Notice that you're putting in the 4 pi here. Remember, the 4 pi represents 2 revolutions in a minute, and the 1/8 is the phase shift that we had to do on the graph. It's now in terms of time, 1/8 of a minute instead of radian measurement. So explain the meaning of the parameters in the coheight function. The amplitude. What is the amplitude? 25. The amplitude is 25. And it's the absolute value of A, which is 25. And the distance between the highest and lowest points, 50 feet. The diameter of the wheel. Of course, you know you only need the distance between the highest point and the midline to come up with the amplitude. So you would cut this one in half. The midline. What is the midline of a trig graph? Does anybody remember? So it's y equals k, and k out here is just plus k, there's no number there, so it's 0. And if it's 0, that means it is the x-axis. So the co-height varies between 25 and negative 25. The phase shift. What does this mean here? What does the phase shift do to a function? Moves it left or right, yes. And in terms of the problem that we're doing here, here's what the explanation is. It means that each 1/4 of a turn takes 1/8 of a minute, which is 12.5 seconds. Without this, car 1 would start in the 3 o'clock position. That's why we had to put that phase shift in there to begin with. Because we don't want to start at the 3 o'clock position, we want to start at the bottom, which is the 6 o'clock position. And then for the period, we've been over this in the last thing, where it's 2 pi over the absolute value of w, and in this case it comes out to be 1/2.